Hello everyone, this is the CDS524 group. Our group name is TiDuXiaFan, and today I'm going to present you this code for our group's diabetes risk prediction models. And this is a completed system for data pre-processing to the mode training, evaluation, and then the web page. I will explain the functionality and the implementation ideas of each part step by step so that you can get a full understanding of how our project works. First, you can see we introduce the diabetes and we define a function to print the clinical integration for the guidelines. It is not just developing a technical model, but it considers how the models can be particularly applied to the healthcare process. It tells the physicians how to use the mode to scan patients, how to take different measures based on the risk scores, and how to integrate the tools with the existing diagnostical process. This demonstration that we are not just doing the technical, but solving the real healthcare problems. And then we do in the data loading and exploration. We load a CSV file and print some basic information which give us a basic understanding of the data, for example, such as how many rows and columns in the data, what the first 5 rows look like, and some statistics such as the average, min-max values and the missing values and other informations. And the next is our data pre-processing part, which is very crucial in machine learning. So in this part of code, doing a couple things. The first, we encode the gender, converting the male and female to 1 and 0. And then we code the target variable class as well, coding the non-diabetes as 0 and P pre-diabetes and Y diabetics as 1. Here we made a simplification by grouping the pre-diabetes and the diabetes together, as they are both concerned from a clinical point of view. And next, we filled the missing value using the median. Why we use the median and not the mean? Because the median is not sensitive to outliers and is most robust. And then we choose some calculus associated with diabetes, such as the age, the euro, the CR, because these features are all indicators that are considered medically relevant to the diabetes. And next, we normalize the features so that we have a mean of 0 and a variance of 1. Doing so eliminates the difference in the magnitude between the different features and allow the model to look at each feature more fairly. And finally, we split the data into the 80% to training and 20% for testing, and use the stratified sampling to ensure that the distribution of the categories in both parts of data was consistent. This avoids the evaluation bias caused by the inconsistent distribution in the training and the testing set. And the next step is mode training and comparison. We trained 3 different machine learning models. The first is logistic regression, the second is random forest, and the last is XGBoost. For each models, we use following evaluation matrix includes accuracy, precision, record, F1 score, and AUC, ROC. Visualization. Next is visualization and evaluation part. We did a lot of visualization to help us understand the models and the data. First, we made a table comparing the performance of 3 models on each of assessments matrix to see which model was the best, and then we draw a category distribution graph to see the proportion of the diabetes and non-diabetes in the data. This was important for us to understand the imbalance in the data. And next, we calculate the wait a second. And next, we calculate the feature importance using the random forest mode to see which medical indicators were most important and for predicting diabetes risk. This is helpful for doctor to understand the risk and the factor for the diabetes. And then we draw a confusion matrix to visualize how the most prediction compares to the real situation. This helps us to find the strengths and weakness of the models. Finally, we also made a correlation heat map to see, yes, here we also create a correlation heat map to see how individual features are related to each other and how they relate to the diabetes. This vulnerable for the understanding of the mechanism of the diabetes. This visualization not only help us evaluate the models, but also provide a visual reference for doctor to help them understand the decision biases of the model. And then it's best mode selecting and saving. We select the best model based on the F1 score, and as the best model because F1 score it takes into account precision and record, which is a more balanced matrix. So we also generate a detailed categorization report for the precision, record, and F1 score for each categories. And then we save the model normalizer and the feature list to the disk so that we could be loaded for use in the real applications. And we finally use the Streamlit to elaborate to build a web interface. I will demonstrate later. So this our group project model can help the doctors identify the high-risk patients earlier and intervenes in a time manner, thereby reducing the indicators of the diabetes and the risk of complications. This is exactly the value of AI in healthcare, not replacing doctors, but helping them to make better decisions. So let's run the code here. Let's run the code, and I have gone ahead and run it using the CMD. You can see the result here. There is also I just mentioned before. So we choose the final model based on the best F1 score. So we choose the random forest here. You can see here's its F1 score was highest, and so we choose the random forest. I will show you the web interface with development using the Streamlit, which is using the oversaved models and which I have run ahead of time in the here. No, here. We can easily access it using the local port. I copy this link and open the edge. And next, I will show you our web interface with development using the Streamlit, which will use our saved models. And I have run ahead of time using the CMD. Here, we can easily copy the link to the local port and run the web page. So our web interface have three main functions. The first is the diabetes risk assessments, which you can enter the relevant indicators for the individual, and it will use the mode we just choose to make a judgment. Here, let's evaluate the risk. It's a little bit slower, I think. Yeah, here are the results. You can see here is the result. You can see it's not only give us the output of the risk, and it also tell us which indicators are not normal. So that let's change the not normal indicators and try again. Here you can see HbA1c was not normal. Let's make it normal. It's changed to 4. Yes, let's evaluate again. Yeah, you can see the risk become low, and you can also upload the CSV file to the bench processing. There is our mode information, and next is our mode information here. Wait. Oh, here you can see there is most information we just mentioned before. We create um, four tables to let us have a more understanding of our model, and our evaluation matrix here is also included here. Wait. So yeah, that's all. And the last part is data visualization. We can upload the CSV file. Let's upload it. Here. Yeah, let's wait a second. So here we can see that the indicators HbA1c distribution, that you can see there is a huge gap between the diabetes and non-diabetes patients. Here, non-diabetes is HbA1c is quite low, and the diabetes it have really high. So and this graph, the next graph is a heat map that we have mentioned before. Wait. Yeah, here, just mentioned before. So and the most important is the last part. Yeah, the last part. The last part, you can select the indicators that you are concerned about, and you can visualize which indicators have the greatest impact of the diabetes and non-diabetes patients. So let's choose some. Choose some randomly. Here, wait a second. Oh, sorry. Here is the results, and how we can see that the differences between the BAM and the HbA1c is particularly large for both populations, and we can determine whether or not these two indicators have a directly impact on whether or not they are diabetes. So let's clear, right? So well, that's all. And for our group project, thanks for watching.